right, so today we talked about the voltaic cell or the galvanic cell. And with the voltaic cell, uses spontaneous redox reactions. So they're split up into two half reactions. What are two half reactions? It's a redox reaction split up by either oxidation or reduction. So got one compartment over here for one half reaction, another compartment over here for another half reaction. Doesn't matter which one you put where. I am going to add each of my electrodes. All right, so if we use the example that we talked about in class, let's say we have zinc reacts with copper ion, producing zinc ion and copper solid. So we can label this electrode as zinc metal, zinc solid. We'll label this electrode as copper. Now we can look at this reaction, and based upon observing it, we can see that zinc undergoes oxidation and copper undergoes reduction. So I'm just going to kind of note that on the side so that I can then go back and label which one is the cathode, which one is the anode. So remember, red cat is a little way to remember that at the cathode we have reduction. So at this particular electrode we call the cathode. Reduction occurs at the cathode. At the anode we have oxidation. So we can say that this electrode, electrons always travel from anode to cathode or negative to positive. We can label the electrodes negative and positive. And the reason why, real quick, why we split up these half reactions is to be able to generate current, to be able to generate electricity. And we need to connect these electrodes with a wire so that electrons can travel through this wire, because that is how the electrons go from one compartment to another. Now, within this compartment, zinc electrode is submerged in a solution that will generate zinc ion, because zinc will end up, from this equation, you can see zinc is producing zinc ion, and over here, copper ion within the solution will produce the copper solid. All right, so we can say over here, copper nitrate, just make sure that whatever solution you choose will generate Cu2+, and whatever solution you use over here will generate Zn2+. Okay, now if we think about this on a molecular level, zinc atom, I say atom to insinuate that it's neutral, zinc solid atom, will give up 2 electrons. So it gives up its 2 electrons, goes up the electrode, out through the wire. But when that happens, this zinc atom that was neutral is now become an ion, so it will go into the solution, that zinc ion. Now, over time, this process will occur and you will end up decreasing in mass. This zinc electrode will decrease in mass because the zinc atom is turning into zinc ion. Now, over time, while this zinc electrode is decreasing in mass, your solution is increasing in zinc ion. And the zinc ion will cause the overall charge of this solution to change. And that's what we are talking about in class. And that's not good. It's gonna hinder the ability of this electron to flow freely. We don't want charge buildup in these different compartments. All right, so this is what's happening on a molecular level. This electron was just given off by zinc oxidation, and copper, there is a pull here. We talked about that today, the potential difference, electrical potential difference that is occurring right there. And these two electrons travel through the wire to this cathode, and at the interface down here, a copper ion in the solution comes and finds these two electrons, combines with the electrons, and actually deposits itself onto this electrode. So over time, what's happening with this copper electrode? Well, it's gaining in mass because it's using up the copper within the solution and becoming copper solid, depositing itself onto this electrode. So if you are losing copper ion while your nitrate ion concentration is not changing, over time the solution will become more negative. So that is why we need a salt bridge to overcome any charge difference within the solutions, because we want neutral solutions. So we have what's called a salt bridge. It can be some type of porous material, and any aqueous salt, sodium chloride or sodium acetate, anything that is aqueous. Now, this solution, remember, will end up becoming negative from the abundance of the nitrate ion because the copper is being taken out of the solution. So what cation from the salt bridge will migrate? Hopefully you chose sodium. You were thinking sodium. Yes, positive will come over here and to cancel out the negative that's starting to add up in the solution. And then the chlorine will come over here, of course, through the bridge, not up and jump over and around, but it'll go through this little salt bridge, migrate its way over here, and start canceling out those extra positive charges that are accumulating in this solution. And by doing that, it'll allow this cell to continue to circulate electrons and produce voltage. All right, so we can actually hook this wire up to a voltmeter to determine the voltage. Or today at the end of class, we figured out how to calculate cell potential by using reduction potentials tabulated in the back of the book. But just wanted to review the voltaic cell. So this is the galvanic cell utilizing spontaneous redox reactions. And we just went through the different parts, labeling them, trying to understand them, and hopefully this helps you.